Hello, dear students. I hope you are doing well. Today, I'm going to talk about visualization of specific energy. This is the last part of the chapter 11, Rapidly Varied Flow. Before starting the visualization part, let's have a recap about specific energy. We already talked that the definition of a specific energy, which is the sum of the depths of flow and velocity head. Uh, in other words, it is the total energy when we consider the channel bed as a lithium. Based on the energy equation and considering loss of energy, we already introduced this equation. You see E1 plus S0 delta x equals to E2 plus SF delta x. The left-hand side shows the total energy. E1 is a specific energy at cross-section 1 or first location, and E2 at right-hand side is the specific energy at second cross-section or second point along the channel. Delta x is the distance between section 1 and 2, S0 delta x, and SF delta x shows the energy losses at each section. We also said that for the case of ignoring the loss of the energy or head loss, and for the horizontal channels, specific energy at entire channel or along the all the channel would be constant, and we can say that E1 equals to E2. We also considered a sudden rise at the bottom of the channel or increasing in the elevation of the bed. For that case, we said that because this sudden change appears in a very short length of the channel, we can neglect friction loss. Therefore, what we will have equality of energy at both sides plus the elevation or height of the hump. We said E1 equals to E2 plus delta Z. This is our delta Z, or here you see that we can say E1 minus delta Y or delta Z equals to E1. Specific energy is the energy at a cross section of an open channel flow with respect to the channel bed. Yes, these are introduction about the definition of a specific energy. And today I would like to talk about the graphical interpretation of specific energy or visualization of specific energy. In a channel with a constant discharge, yes, we assume that we have a constant discharge in a channel, and uh, we are going to draw the specific energy. We know that discharge equals to A1 V1. Therefore, along a channel for a constant discharge, we will have the this rule: production of area times velocity is constant because it gives you the value of discharge. We already said that specific energy is the summation of flow depth plus velocity head. Therefore, E equals to Y plus V square over 2G. For any shape of channel, we can replace V square with Q2 over A2 because Q equals to A times V. Therefore, we can rewrite specific energy in this form: E equals to Y plus Q square over 2G A square. And we know that uh, area, surface area is a function of y. So if our cross section is rectangular, we can use the term unit discharge per unit width q, lowercase q, that we already talked about it, and we know that this area equals to by. Therefore we can write that capital Q equals to unit discharge time bottom width. B is bottom width, and using these definitions of Q and A equals to by, uh, then replacing the relevant values in this term of the specific energy, we can rewrite specific energy in terms of discharge per unit width for rectangular cross sections. Therefore, you can say that E equals to um, y plus q square over 2gy square. We already discussed about such equations, and we said that this is a cubic equation with three roots, and we saw that one of the roots was negative. Therefore we can neglect from that root. This is mathematically true, but physically not acceptable, because we don't have um, negative depths of flow. So here we have a simple question. It's asked about how many possible depths. Yes, from 3, when we know that 1 is negative, therefore we will have two specific uh, depths for a given specific energy. uh, for we will have two specific depths for one specific energy. I already in previous lectures I told that I will talk about how it is possible we will have two specific depths, and which one is correct. I told that it depends on the flow regime. And we saw some examples that when flow regime is subcritical or supercritical, critical depth is the uh, threshold, is the value that dictates which of those two values is correct for our problem. Okay, to visually present specific energy, I used Microsoft Excel to draw the specific energy diagram, which is also sometimes called SED diagram or SED. Um as I told, we assume a given discharge. Here I assume that discharge is 4, and for the case of simplicity of calculations, I considered a rectangular cross section with a bottom width equals to top width and equals to 2 meters. Therefore, for this cross section, I'm going to depict the specific energy diagram. How can I do it? Easily, I can, with respect to the this equation, specific energy equation, I can draw this equation numerically. How, as you see here in my Excel file, I created 5 columns, each of which represent one um, feature of a specific energy, or one element of a specific energy. The first column is y, depth of the flow in meter. The second column is area. For each depth, I will have a specific area in this cross section. Then, as I have discharge value, I can calculate velocity. This is third column, and when I have velocity, I can calculate velocity head here. As you see equals to v square over 2g. And now with these four columns with a yellow head, I have uh, both terms of the specific energy y and v square over 2g. Therefore, I can sum column A and column D to get a specific energy for the assumed y and the given q in this rectangular cross section. Uh, I um, gave some Ys, as you see, with the 0.10 or 10 centimeter steps. First assumption y equals to 0.1, second 0.2, 0.3, 0.4, 0.5. And for each of these y's, I can multiply y by given top feed equals to 2 meter. For example, if I multiply 0.1 with 2, it gives me a surface area of 0.2. And if I divide 4 by 0.2, my velocity will be 20 meter per second. And now I can square it, then divide it by 2g. It gives me velocity head. And the velocity head for the case of y equals to 0.1 is 20.4. Now I can add the value of y with the velocity head, which will be 20.5. My um, specific energy for y equals to zero point 0.1. Therefore, I have one point which I can come to a diagram and show this point in a such diagram in which my x-axis is specific energy and my y-axis is flow depth or y. You need as the depth is vertical. This is why here we use vertical axis as a y. Therefore, for y 0.1, something like here, for example, this is 0, this is 1, 2, 3, 4, 5. Therefore, 0.5 is somewhere too close to the y equals to 0. And for such point, my E should be 24.5, which would be here, for example. And therefore, this is my first point. I can find the energy for different phi's, like for 0.2, for 0.3, 4, 5, and for each phi, I can find the corresponding uh, specific energy as a dot on this diagram. Then I can uh, connect these dots together to reach a specific energy diagram, and you will see that the final shape of or combination of these dots periods are such a or provide such a diagram. The important thing which I want to talk is the looking to the variation of elevation with respect to the y. You see here that here I increased y, increased 10 centimeter. However, let's see the variation of a specific energy. Here for first y, I have 20 meter as a specific energy, but when I increase only 10 centimeter of the flow depth, specific energy suddenly decreases to be about 5.3. Let's see where is this point in our diagram. 5.3. 5.3, somewhere here. Yes, somewhere here. Yes, for when the 5.3 somewhere here, and the corresponding y is zero point 0.2. You see, even I have very low depth, and my energy reduced from 20 for 5.3. I increase the depth. You see, again I have a decrease, or my energy, specific energy, will decrease to be 2.5, somewhere here. Yes, between 0 and 5, somewhere here, which associate to the y equal to zero point 0.3. When the y is zero point 0.4, I will have a value of E equals to 1.67, and it would be somewhere like again here. And you see that by increasing, again I have a decrease in the value of E. Again I increase the value of Y, and I have a lower specific energy and lower specific energy. But in this point, for the y equals to zero point 0.7, zero point 0.8, my specific energy is 1.12, and this is the minimum value of specific energy. Then after y equals to zero point 0.8, my specific energy increases. Instead of 1.12, I have 15, 20, 25, and increases by, again, by increasing the y, specific energy increases. You see that this is therefore minimum point, or a minimum specific energy, which belongs to somewhere here, about y equals to the depths of the 0.7, 0.75, or zero point 0.8. If you have more digits, you will find which one is greater. And I assume that, for example, 0.75 is the depth that creates the minimum specific energy. After that, you saw that our specific energy increases, and this is why our specific energy again increases, because this is our increasing way, and in this way increases. And look here, for example, when y equals to 2 meter, yes, somewhere here, y equals to 2 meter, specific energy is so close to y, it will be equal to 2 meter again. And it can say that, for example, for 2.1 it is equal to 2.1, for 2.2 specific energy equals 2.2. And if you check all these first and last column, even for 3 meter, even for 4 meter, 5 meter, 10 meter to 15, 20, and you see that these two columns are so close together, and they create y equals to E line, or for a 1 line, 45-degree line. Therefore we have a line, therefore this limb of the specific energy, or this arm of specific energy, uh, is uh, goes to mm, be equal to y equals to goes to have a equation like y equals to em. And you see that from 5, I increased my y with higher uh, variation from 5, 10, 15, to show that how, by increasing the values, this line, or this arm of the specific energy diagram would be the tangent to 1 1 line, or y equals to E line. So this is a specific energy diagram, and this for all the cross section, the diagram, the shape of the specific energy is more or less similar to this shape. And uh, you see that if I draw a one line, by mean that I assume that if it is our x-axis, y equals to x-axis or 45-degree line, you see that a specific energy always fall into the right hand of one line. The values are always positive. Yes, we know this is a specific energy. Both are in terms of meter, and um, one arm of this diagram is tangent to the 1 line. I will talk more about this diagram in the next slides. Therefore, uh, I think for this slide, the given information is enough, and this shape is something that you should memorize it and always know that specific energy has a one minimum. It always is in right hand side of the 1 line, and it includes two terms, y and v square. And um, for lower value of y, you see that for the lower value of y, v square over 2g is higher, and for higher value of I, v square over 2g is lower. These are in agreement with the concept of uh, q equals to a times v when you increases area by increasing the flow depth. Therefore, velocity will consequently decreases, and its square form will decreases with higher rate. And we can also um, imply this result that for lower velocities, for lower depths, velocity is the main or dominant term in a specific energy, and it might be the supercritical flow condition where we know flow has the higher velocity. And by contrast, for higher depths, as you see, for higher depths, velocity is very low, and therefore velocity head is negligible. You see, for depths more than 5 meter, we can neglect velocity head in a specific energy. Okay, now I would like to ask a question where the minimum point is along the specific energy curve. Yes, the question here focused on just this point. You see here that I was able to find the location or corresponding depths for the minimum value of a specific energy curve. But I solved numerically how we can find this point mathematically. This is possible to answer this question very easily. If you know the equation of specific energy, you can take its derivative to find its minimum value, or to determine for which y the specific energy in a given cross section is minimum. Here, what we must do, we must take derivative of a specific energy in terms of y. We know that from here, for example, we know that E is a function of y, and also velocity is a function of y. But when we have a discharge, for a given discharge, we can replace velocity with q over a. For a constant q, we can write this equation. Yes, So my equation is like this. Specific energy equals to y plus q square over 2ga square. And I want to find the minimum value of E, specific energy. Uh, and for this, I will take a derivative of dE over dy. Therefore, dE over dy equals to d over dy of this term. Yes, y plus q square over 2ga square. And I can take derivative of first term and also add it with the derivative of second term. D over dy over dy would be 1. Therefore, I will have 1 plus d over dy of this term. And you know that q is a constant. First, we assumed for a given q. 2g is a constant. Therefore, d over dy q square over 2ga square equals to d over dy, q2 over 2g times d over dy of 1 over a square. And therefore, you should find the derivative of 1 over a square over 2 dy with respect to the y. And easily you see here, I know that if y equals to 1 over 1 squared dy would be dy over dA would be minus 2 over a to the power of 3. The process is given here. With a little algebra, you can change a 1 over a squared to be a over minus 2, and you know how to take a derivative of such a simple equation. Anyway, d over dy over dA equals to minus 2 over a3. Therefore, I will have 1 minus 2q square over 2g a to the power of 3 times dA over di. Now, I calculated d over dy of this term, which is also in the results. I have dA over di. To find dr over di, your knowledge from fluid mechanics may help you. If you remember, dA or differential area for any cross section, for a given cross section like this, can be assumed at the top of the channel. I assume that this is top of the cross section, which is T or B, let's say B or T. The For a differential depth equals to dy, the corresponding area would be differential area, and differential area would be b times dy. Therefore, differential area equals b times dy, and I can replace dA over dy with b. Yes, dA over dy would be b. And if I write here b, and if I set these terms equal to 0, because I'm looking for the minimum value of the specific energy, what I have this equation: q to p over ga to the power of 3 equals 1. Yes, this is the uh, condition that shows me dE over dy equals 0. I know that q2 over a square equals to v square. Yes, q square over a square is v square. And a square, if I replace q2 over a to the power 3, I should write v square, and I have a at denominator, and at up I will have this equation would be v square b over ga. Therefore, I have a b at as a in numerator. I have a at uh, denominator, and you know that A over B, here B is top width, yes. A over B uh, equals to mean depth, yes. Mean depth. And here I have B over A, therefore I should write instead of D, 1 over D, and therefore this equation would be equal to V squared over G dm. As I told, dm is the uh, hydraulic mean depth, and this formula must be familiar to you, and you might know that V over the square root of GD equals to third number, yes? Therefore, V square over GD is the third square. And for this example, for this condition, third square equals to 1. Or let's say third number equals to 1. And this is also familiar to you. When the third number is 1, you know that this is the critical flow condition where velocity equals to square root of the uh, GDM. And from here, we can get this conclusion. At the critical depths, the specific energy is the minimum. In other words, the answer for this question, where the minimum point is along the ES curve, the answer is critical depths. In this diagram, you can easily understand what we did. We take a derivative of the relevant function of this diagram, and we found that when E equals to its minimum, it gets its minimum value, the H or corresponding depth equals to YC or HC. Anyway, it is called critical depth. As it is critical depth, the minimum specific energy is sometimes called critical specific energy, and we can show it with E sub C or E minimum or E min. This example gives us some new findings about uh, the specific energy curve. We know that the minimum value of the curve happens, or sorry, minimum value of the specific energy in any cross section occurs when the depth of flow equals to critical depth. So for the depths above the critical depths, I have subcritical flow condition. Yes, for the depths more than HC, for depths like here, 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 I have subcritical flow condition. Therefore, if I separate specific energy diagram in two parts above the hydraulic depths, above the critical depths and below the critical depths. This zone is a zone that fluid is less than 1, which is called subcritical flow zone. This is subcritical flow zone. What does it mean? It means that when in this cross section, or for any cross section that you draw this specific energy, if the flow depth is higher than this, your specific energy, has the value that can be read from this x-axis or e-axis, and this zone is subcritical flow zone. By contrast, for any flow depths in the channel less than HC, this zone you see here, this zone is supercritical flow zone, which is shown by Froude number more than 1. Therefore, uh, we can say that a specific energy diagram has one minimum, a horizontal line which crosses this minimum shows the depths of critical flow condition, and this horizontal line divides our zone within the specific energy diagram for subcritical zone and supercritical zone, which are in above and below the uh, horizontal line respectively. This is not all about the specific energy diagram. I will talk more and more, maybe in next sessions also. However, in the next slide, I will come back and talk about features of specific energy diagram. Now I know that minimum specific energy of minimum specific energy at any channel appears or happens at the condition of critical flow velocity. So we are going to calculate the value of specific energy for a rectangular cross section, or to find minimum specific energy, or you can say critical specific energy in rectangular cross section. What we should do, this process is completely same as the process that we already did for general cross section. But for rectangular cross section, we have a simplification condition where we can replace Q by capital Q by lowercase q, or discharge with discharge per unit width. Therefore, I can write E equals to, or specific energy equals to y plus q square over 2gy square. As the previous slide, we should take derivative of E with respect to the y and set this derivative equals to 0. For this equation, dE over dy can be easily find equals to 1 plus 1 minus q square over gy square. Don't forget that q is a constant like uh, capital Q, 2g is constant, therefore I must find the derivative of 1 over y square equals to minus 1 over y to the power of 3. Therefore, this must be 0, and which gives me q square over gy to the power 2 equals to 1. And you also uh, might be familiar with this. If you not, come back to the uh, previous lectures, and you will see that for rectangular cross section, this condition give me critical depths. Okay, now I can say that uh, I this condition, if used for the specific energy, it gives me the value of critical energy, because this is for the case that the energy is minimum, specific energy is minimum. Here I repeated the main specific energy formula for rectangular cross sections, and here what I did, I only said that um, I can divide y plus 1 over 2 outside, and I multiplied y square with one y square here, and with one, sorry, with one y here and another y here, or both numerator and denominator multiplied by y. And here you see that the I have y to the power of 3 at denominator, and 1 y here I wrote by h. This is the same, just is assume it is a y, not h, or it can be h or y. Both are the same, and if you can remove with this h with one of y's here, and to have the same equation here. So this q squared over gy to the power of 3, from derivative we know that equals to 1. Therefore I can replace or remove this term. What will be remain will be remain y plus 1 half of h or y. uh, Here again, I forgot to correct this equation. I'm so sorry, but assume that from the beginning you can assume that I replaced y with h. Okay, therefore I have h plus half of h, and finally you can reach such a solution. The specific energy equals to uh, 3 over 2 times h, or 1.5 h. And as this h obtained with derivative of the E specific over y, this is your critical depth. Therefore, you can say that critical energy, or critical minimum energy, minimum specific energy, equal at rectangular cross sections equal 1.5 uh, times critical depth. And here also you can find y, or you can solve this equation for y, which gives you this equation. Yes, hc equals to q squared over g to the power of 1/3, and you know this is the magic formula that we use to find critical depths in rectangular channels. These two equations are very important, and I suggest you to memorize these two equations. In summary, we can say that critical depth in rectangular channels equals to for a given discharge, and for a known bottom width, critical depths can easily calculated by lowercase q square over g to the power of 1/3. And if no if you know uh, critical depths, you can find minimum energy, minimum specific energy for that cross section, which is equals to 3 uh, over 2 hc. Yes, now I would like to come back to the specific energy diagram and define one new concept, which is called alternate depths. We already saw that for a given specific energy, we can have two different depths in a channel. One is uh, below the critical depths, and the other is above the critical depths. Here you see this is a given energy. For example, this is my energy line, which is greater than minimum energy. And you see that this vertical line crosses the specific energy at 2 points. Therefore, these each of these points, one always is below the HC, the other is always above the critical depths HC. These two depths, this is 1 and this is 2, are called alternate depths. Let's discuss this issue here with some numerical values. This is uh, a specific energy diagram for any given cross-sectional any given cross-section. Okay, I know that this is my 1 line, my specific energy diagram. This is my specific energy diagram, and uh, for any given uh, specific energy, not any, always for energy is more than this minimum, each specific energy will cross my each specific energy will cross the diagram at 2 points. Each point you see, these are the alternate points and alternate depths, and associated depths are shown here. One depth is about 0.9, the other depth about 2.8. Yes. So as we already told, one of these depths is below the critical depths, the other is above the critical depths. I want to show you some information about the numerical values of a specific diagram at these two depths. We know that this is the minimum specific energy value, yes, and the corresponding edge is somewhere here, yes. Let's say 1.5. This is our critical depth, and you see that this point is below the critical depth. Therefore, this is the zone of the supercritical flow condition. This is zone of the subcritical flow condition. This point energy, or for this depth 0.9, when the flow depth is 0.9, energy, corresponding specific energy, equals to 3 meters. Yes, 3 meters. Just for this value, I can find the 3 meters. And when the flow depth equals to 2.8, again, I can find the specific energy equal to 3 meters. The important point here is this: when flow depth equals to 0.9, only this part of entire specific energy is y part, and this remaining, or this larger part, shows v square over 2g. Yes, we know that a specific energy is the summation of y, or depth, plus velocity head. You see here, for this point, specific energy is summation of two terms. One terms e y plus v2 over y squared. Why this is from here to here? Why? Because this yellow line is my y equals to e line. Yes, at this point I know that y equals to a specific energy from here, and I know that my entire specific energy is the summation of energy from here to here plus energy from here to here. The corresponding energy, the corresponding part for y from here to here therefore would be somewhere here, as we assumed it is about zero point 0.9. And this remaining energy that I showed here shows the value of V squared over 2G. Here you see that for supercritical flow condition, because you know that I am below the critical depths. Yes, here is the critical depths. I am below the critical depths. Therefore, velocity is more dominant in total energy or in specific energy. Yes, and head has lower impact. By contrast, let's go to the FR less than 1, this zone, yes, subcritical energy zone. In subcritical energy zone, we said that flow has a higher depth, therefore, most part or dominant part of the specific energy would be depth, and velocity will have lower role in the entire specific energy. You see here to here, from 0 to the y equals to E line shows the y term of specific energy, and this small part between the 1 line and our point, this small horizontal part, or I showed here with some magnifying, shows the velocity head, which is very low. Yes, these are some information about the specific energy diagram, very useful for interpretation of solution of problems that we solved for a sudden hump in a channel. I will talk more about this in the next chapter when we evaluate hydraulic jumps.